composition.
Do tell me when you're going, like, pressing the light.
I pressed the button. Button has been pressed.
Ah.
You're now being recorded forever in all history.
Oh God.
Oh God.
What would the children think?
What would the...
No, yeah, so do you want to, like, just get into it?
Yeah, I think so. I'm gonna pop out the chat in case anyone ends up joining.
Beat you to it.
All right.
So whenever you, like, pop up the drawing thing.
All right, we got the drawing.
Write down a few things.
All right, we got the drawing, we got the music, we got the experts. All right, let's learn about types. So
Yes,
we're gonna learn
types.
about types.
We're gonna
Fuck
start with
types.
the
I don't
very-
care about types. I just want my Python and JavaScript. Why do I care about types?
Yes. Well, first of all, secretly, Java also has types. JavaScript.
Yeah, right.
Yeah. And there, side series will not like this, but a type can probably best be described as, in a programming context, as a way of interpreting data. That's why it's often also referred to as a data type. Although data types don't really incorporate functions usually. But I'm getting out of myself.
All right, let's talk about Lambda. We were talking about Lambda calculus first and how that relates to types.
We're gonna start with the simple stuff.
Okay, simple
you-
stuff. All right,
you
I
can
see
have
values
stuff
and types.
Values and types. So we have a value like 1. Can you tell me the type of 1?
Type. So my intuition says that the type is going to be a number, but that's like JavaScript. Maybe I'm like a JavaScript developer, and when I think of type of 1, I think of number. Right? That's the type. It's the type number. Am I wrong?
Yeah. Well, you're sort of getting there.
Mm-hmm.
Because the thing about number already is number is a very general type that can store a lot of different stuff. When we talk about programming, what you will often see is something like, I just realized I do not see what you have written.
Really? You can't see that?
No.
Oh, that's strange. If
It
I
says number there, but
if I reload.
that might be a thing.
Oh, I still see. Oh, okay. I
Now,
just need to reload.
now it did load in number. Yeah.
Wow, this is so broken.
Yeah, it'll be fine.
All right.
So, oh god, yeah, I need to do the thing. So if we look at numbers, then we can see different types of numbers. You might have heard of int before.
Int as an integer.
Yes. And
Which is the set of all numbers, set of all real numbers from negative infinity to positive infinity.
yes.
Excellent. And then
Exactly.
float is the set of all real numbers. Well, with the storage limitation of how float is implemented from negative infinity to, or no, I guess yeah, that's interesting. Thinking about how these types like kind of relate to hardware limitations, because there's the mathematical perception of it, but then there's like the hardware thing.
Yeah, so in JavaScript, the distinction is very different. In most programming languages, we usually only distinguish between ints and some sort of floating point number, where floating point numbers are like 6 or like 0.0 or 28.12, like decimal points. However, there are also other types of numbers. Like you can go much more general than this. You also have like these whole branches in mathematics considering, for example, irrational numbers like the number pi, which is not usually we express those as a float or a double in programming, because realistically speaking, you don't need that many digits of pi. But for like doing mathematics, this might be difficult. So this just shows that knowing about these types and working with them can be fairly important. In most programming languages, you distinguish between like ints or like floating point numbers. And a nice thing about, for example, something like Haskell, they do away with this like float and double thing, and they just give you a infinite precision. Meaning they will look at how you use this number and adjust the precision of the calculation steps accordingly.
So it's like it's intelligent, somewhat about like
yeah. I believe Python also does this for integers, where you can have infinite precision integers. Don't quote me on that. But yes, numbers is a very good guess. You get a check mark from.
Yeah, so green check mark. Excellent.
What would be the type of hello?
Hello. Well, let's see. I've done some TypeScript, and so I'm going to say that is a string. String. Oh, I see. String.
This is, in fact, a string.
Excellent.
Do you know how we often represent strings?
How do we often represent strings?
What is a string really?
A string is a collection of individual characters that come together as a string. So it's like individual little guys that come together.
This is often this is also seen as a list of characters. And this distinction between something being a string or something being a list of characters, this really depends on how this is implemented and how you use this behind the scenes. So you can have strings, you can this. To round off the other common types, we have like single characters, which would just be a char. And then usually you have booleans, which are...
How cool is it that like George Boole is like he has his name in like every some form of his name in like every language pretty much. Like,
I had no idea that was...
Yeah, George Boole, like that's his name, and he's in like every programming language. It's sick.
Wow.
Yeah, I want to be that dude.
That's... Well, good luck.
Yeah, right. Yeah, I don't know the guy who invented strings and stuff, but I bet you he was a real character.
What about Tuesday?
Tuesday. Oh, weird. Tuesday. Well, you got strings, you got characters, We have Boolean, which is true. Tuesday doesn't have any quotes around it. So I think my human intuition is that it's like a day of the week. Tuesday, the type of Tuesday is the day of the week. That's how I have it like expressed in my head.
It can in fact be a weekday.
Weekday, yeah.
The thing about weekday is that most programming languages do not define a data type for this.
Mm.
So you will often have to define your own.
Right.
Usually you use something like an enumerator for this in most languages. The
Right.
nice thing about...
I would have like a const. I guess I'm thinking of how I would do this maybe in Go, is I would have like a bunch of like constant variables called like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And I would like group those all by saying like their like underlying type that they are is weekday.
Yes.
And all of those things are
And-
equal to some number or some string. It could be the string representation of Tuesday or something like that.
Yeah. And for example, in Java, you have a construct called an enumerator, where you can basically provide these list of things, and it will automatically assign all of them a number and keep track for you. So you can use this. So this is a very general trick. The nice thing is, in most functional programming languages, you get to define your own data type. So you can say like, hey, a weekday is either Monday or Tuesday or Friday or all the days of the week.
Mm-hmm.
Which is in a way useful, because in what you mentioned, with your technique, do you think there's a difference between these like string, char, character, bool, number things and your weekday?
Is there a relationship between string characters, bool, and what a weekday is?
Are they somehow different? Is there any... Are they the same? Do they behave the same?
I think conceptually they express the same like category, like categorical representation, but how I would use them would look very differently.
Yeah. And the most notable thing about what you described is that you're basically encoding this weekday thing in terms of numbers.
Mm-hmm.
Yeah,
integers. Right. Usually that's how I do it in my programming language.
Yeah. And that works. And the nice advantage of that is that your like CPU, your physical hardware, knows how to encode these things and how to work with these things in numbers.
Mm-hmm.
So on that side is all fine. However, when you actually write the code, you need to take care that whenever you want a function that does something based on a weekday, the type of that thing would actually be a number. And then what is preventing me from adding in weekday 27, for example?
Mm-hmm.
That can be a very, challenging thing to work with. And especially with these like enum things like you're showing now, you need to sort of keep telling the program to work with this appropriately. And you need to use this like weekday.monday thing.
Yeah. Yeah, you're accessing
The nice
like
thing
the
about...
type, the underlying type, which is weekday, and then you're grabbing that specific value from weekday, which is Monday, every time you want to use it.
Yeah. And
which feels good. That feels like that works. Like that's reasonable to me. Like it feels very intuitive.
But when you really start looking at this, you're effectively defining a class called weekday, and then you're using the look into this class operator, which is the dot, to get out the value of Monday.
Right.
Which is different. So in that sense, weekday is on a different level in your type system than these like string, character, boolean, because you need to do this like extra step. The nice thing about like pure functional languages like Haskell is you can define weekday in such a way that it will be treated as if it was built in the first place. So you will not have to do these like extra tricks, and then you can just use Tuesday as is as a value.
So I wouldn't do weekday.monday anymore. It would just be. Actually, let's see.
No,
ChatGPT.
for example, if you ask ChatGPT how to make a data type for weekdays in Haskell.
ChatGPT is so cool. I find it's such a cool way to teach.
Yeah. So if we look at the top, in the code block, only the first line is really something you need to care about. It just says like, hey, weekday is one of these things. And then you can see where it actually uses that code. It says like, hey, we have Monday.
Yeah.
And then a nice thing that it does, it says deriving show and enum. That just basically means, hey, let's give us some code to actually, well, show the thing. That's basically a toString. And the enum allows you to enumerate through it, which is not actually used in this case.
So I think that the big thing here that stands out in the two code examples is the fact, like you said, like we're no longer doing weekday.monday. It's just Monday.
Yes.
And that
really enforces this, like, this is on the same level.
Yeah. Like this is like ingrained with like the language. It's like it's not like an afterthought. Like the implementation of weekday is not like, oh, it's like an enum weekday. It is like, no, it's the type weekday and Monday is the thing. Abs. We're going to give some abs to X. We're going to do some crunches.
This is a basic version of giving the absolute value of something. What would be the type of this?
What would be the type of absolute value of X? Well, if I want to get the absolute value of something, I want X to be a number. So, but now, like it's like you have a number going into some like operation, which it's like it's a function. So it's like a function takes X, which is a number, and then it's going to return another number.
Precisely. And we usually write that down as, let's assume we're working with int because it's fewer characters for me to write.
Right. It is int, but theoretically you could use any of our different number types there because we have int, but there's also float and double.
Yeah.
So theoretically that would work. But yeah, we'll save some writing.
To make this even, you can make this general and basically say it doesn't matter what this thing is, as long as the square and the square root is defined on it, we're safe. We can use it.
Mm-hmm.
So you could even make this more general, saying like, oh, this can be used on any data types which have these operations defined for them.
Right.
And that way you can make it even more. But for now, let's keep it simple and keep it on Intuit. Do you think this thing is in type different from what we have above?
Is that a different type? Well, I haven't seen the arrow before.
Is there a meaningful
difference? It's still just like a type, but now we have like the arrow that's like combining two types or transforming one type into the same type.
Yeah, this is what we would call a like. It's effectively a composite type. So like a type made up of other types. A very nice example of such a type is this is a tuple of 4,3.
Hmm.
What do you think the type would be?
It is a list of two elements of two integers. Because we only got two things in there, and both of them are numbers, which we're shorthanding for int right now.
Yeah, so we can define the type as being int, int.
Yeah.
The nice thing is if I take something like can you give me the type of this one?
That would be similar to the top one, except the second int is now a string. So
exactly.
Int and a string. Which we've already defined before. We already know what all those types are.
Yeah.
We're just compiling them together.
Yeah. So the thing about this is this like tuple thing is usually in most languages they support tuples in some internal level.
Mm-hmm.
As in you can make a function that takes as argument a tuple. And most programming languages you can also return a tuple.
Mm-hmm.
So you can basically work with these things of this data type in the same way you can work with something of type bool in expressing something. And like we've shown with this weekday thing, it's slightly different than working with bool because usually it doesn't have support. But for a language like Haskell, it has support. So you can use weekday in the same way you would use booleans or strings or characters without that being meaningfully different.
Right.
Can you do the same thing for these functions?
Can you say that one more time?
Can you use these something of this type? So in the same way you can use something like a boolean or a character or a string or a number.
I guess why not? Like it seems
that's exactly the point.
Right. It's all just a type, and a type can go wherever a type can go. Because a type is really kind of like it's the ultimate way of like combining all of these other types together. Because it's like you got to type number, you got to type string, you got to type char, you got to type bool.
Yeah.
So if we're defining like something of like our composite type, there is just something that can have two different types, then why not? You could put anything in there.
And I wouldn't call them ultimate types because these types are still basic, but you can do a lot more of these types. But yes, that's the idea. However, in most programming language, you cannot simply use a function as an argument for something.
Mm-hmm.
Or pass that through. Or like when you're calling another function, define a function right there.
What do you mean? I can just pass functions in JavaScript. I write callbacks all the time. Write me JavaScript that passes callbacks around. We love callbacks.
I'm going to have a look at this.
You know how we just shove like functions because it's like JavaScript is like, yeah, sure. Like you can shove that in there.
Yeah. Oh, yeah.
I don't care. You just call that function. What does it do? What is the return type? I have no idea, but you can just put that in there. And so it's going to display it.
Yeah.
And look, I look at this. So I'm looking this and I'm like, cool. Like, I can like kind of follow along. Like if I was like more of a beginner developer and it's like I've learned a little bit of JavaScript, I can go around. Cool. Like I got something working here. Like I have a website that now like asynchronously makes something happen every second. So like how does types relate to that? Like why would I care about types? Like
yes,
if I can make something run like this so easily in my browser.
So the thing about types is you can assign everything a type.
Mm-hmm.
So you can write a type for this expression that you've just made. I will not attempt that because it seems complicated.
And we can
And we're not
well
there
ask
yet.
ChatGPT. Write me the Haskell type for the code above. So let's see.
Oh, I am very skeptical.
Yeah, let's see. I have no idea.
It's already doing stuff which is far from what I've gone to. But
All right. So process number.
I mean, sure.
We have int. All right. So process number. We got a number and then the callback.
Yeah.
Yeah. So an int, and then
We're skipping steps.
we're skipping steps,
then,
but we are getting close to it, right? We do have the foundation. We don't know what IO is yet, but theoretically, it's on the same level as int, and so it's more or less going to be the same process of explaining and expressing the types that we've done before. And
I'm not explaining the IO monad. That's a step too far.
Yeah, right. Oh, yeah, that is true. IO is a little unhinged, but
yeah,
it is interesting.
It's
so
fine, but it's like we're not there yet.
We're not there yet, but we do have some foundation that could start to address like what it is that we're looking at here.
So, what you will see in most languages is like this giving functions as arguments or returning functions as the result of a function. Like you've seen before, that is non-functional languages shoehorning in functional stuff afterwards. Because like standard plain old JavaScript doesn't support this. This is later standard.
What do you mean?
stuff.
We got types. We have TypeScript.
Yeah, but like the thing with TypeScript is you took JavaScript and you were like, we should have given this types, and then you're like, let's shove them in anyway.
Let's make it Turing complete too, so we can play tic-tac-toe in just the type system. Beautiful.
Yes.
Absolutely beautiful.
So these are these types, and the idea with like pure functional languages is that all these types are in fact on the same level.
Mm-hmm.
And that means that in writing a program, it shouldn't really differ in the sense that I lost my sentence. Let me try that again.
All right. Do it live. We'll clip it.
When you're working with types, you can use a function in the same sense that you would use a Boolean. So writing a function that returns another function is not any different from writing a function that returns just an integer or a Boolean.
Okay.
And allowing you to treat all of these at the same level is a really powerful construct, which really helps your expressiveness, because you're no longer dealing with all of these sort of hacky workarounds like taking your weekdays and putting them in a list corresponding to integers, and then you're no longer sure if you're working with integers. Stuff like that.
You just slowly like fall into like the void, and you're just like, oh, like no more types.
Yeah. So let's get to the first thing. If we remember how I wrote down this absolute function, the first thing we're going to do is we're going to write it down differently. So the main difference here is we do the same thing as we did before. However, we take our function name, we put it at the front. Then we give our arguments. And then we follow that by how these arguments should be combined. So this is essentially the same. It just gets rid of all the unnecessary brackets. And this will be useful for later. For example, if we define a plus function, we can take x, we can take y, and we say x plus y,
Mm-hmm.
which is just sort of renaming this operator plus. But we can make this a weird plus function. We say like every time we do an addition, we're going to add 3 as well. Because no reason. Could you give me the type of this function?
The type of the plus function?
Yes.
Oh. Okay. Well, I don't have any context clues from what plus. Well, okay, so I'm using my brain, and like my brain is interpreting plus as something that deals with math, but there's nothing about x and y that would, on the left hand side of the equal sign, that would suggest that. So I look to the right.
You can assume that we're working with integers still. We'll make it more generic later.
We're still, yeah, but it's like theoretically, like I look on the left side and it's like, yeah, my human brain like will just say that it's like 2 integers, so it's probably going to look similar to the one that we did for absolute value, except there's like one more int arrow sign before all of that. So it's like int arrow, because I have like an integer and then another integer, and then that's going to create another integer.
So if we define the type, wait, let me check something real quick. So I use consistent notation. Because that is a pain if you're working like 4 different languages that all do the same thing.
Oh yeah. You can do
so
that's ChatGPT.
Whenever we're gonna not do Haskell syntax now. We're gonna do Elm syntax. That will be fair. Important later.
Yeah.
So we say plus, and then we use the colon to indicate that we're working with a type. You're saying int arrow int for the type.
Yeah.
Yeah.
And then but that's just like the first int is like x, the second int is y, but then there's also the return type, which is an int, which is the thing that happens when you add x and y and 3 together.
So how should I write that down?
I think from my knowledge of Haskell and types that it's another arrow int.
Exactly. So
which that feels a little strange. That like I remember seeing this before, like originally, and being like, this is like looks a little confusing. So it might be helpful to like break down like why we write it like that.
We can do this. And if I say we can do this, is some programming languages do this. They say you have 2 integers as input, and we produce 1 integer as output. That is what you would expect from a plus function.
Yeah.
Does this more sense?
Yeah, that makes sense.
Okay. So I will explain why we write this arrow here anyways. For now, just think about it as basically what you can do. You can split this up into boxes between the arrows. And then the very last one will be the return type. And all the other ones will be the arguments.
Yeah, that's a good grouping. I like that.
And this is how most people think of these types. There is a good reason for this extra arrow, but I'm going to hold off on that for just a little bit. So we can sort of...
This is very confusing. I thought we were talking about programming. This is starting to look like math class.
Well, we're still defining a function. Like this is Haskell code. You can plop this in Haskell. Well, you need to add another code. You can plop this in Elm. It will work.
Right. Beauty comes with some level of contextual understanding.
Yes.
We're trying to get there. We're trying to get to the beautiful future where everything's functional.
So So what we can do is we can look at two functions or two values. And the weird thing here is that actually every value you could sort of interpret as being a function. There is no real difference between like a value that takes no arguments and produces an int, or just being an int.
Mm-hmm.
Because this value thing might be defined as being 4 plus 7. Because the type of 4 plus 7, the type of that is still int. Because it's not a function. I hope this is clear.
4 plus 7
4
because there's no like variables. It's just like the number, the integer 4, the integer 7 coming together.
Yeah. This is exactly equivalent as, well, what's 4 plus 7?
11. I knew that.
This is exactly equivalent to 11. And if two things are equivalent, they have the same type, by definition.
Okay.
Yeah. For some definition of equivalence, like
yeah, right, exactly.
Hang me for that.
Isomorphic, right? Isn't that like some type of equivalence?
I'm not going to go into it.
Yeah,
it's
not worth.
It's a whole like no.
No.
So we have this abs and this value. Oh, I should explain one more thing first. Yeah. If we look at abs and we look again at our original definition of abs, what does this evaluate to?
So 4 is going to be x, so x squared is 16, and then the square root of 16 is 4. So 4.
Precisely. And the same for minus 4 would also be 4. This is how you do it. If we look at our definition of plus, what would be the type of this?
Plus 5 and 7, that's an int. Or yeah, the whole type.
Sorry, what does it? The int. This is an int.
Just one int, right? Because we evaluate. We know exactly what it is.
Yeah, because this evaluates to
12, which is just an int.
Which is just an int. The thing I want you to note here is that if we want to apply a function to an argument, note how we do not do this.
Right, because this is something that I was actually like kind of thinking of before, is when we were writing the tuples, like I'm realizing that that's how we traditionally in programming kind of like write like arguments for a function. But because now we have the arrow syntax, it's like completely different. And that's why it starts feeling more like math or something like that. It starts to feel like something that's like much more foreign, because it's like C-like languages express parameters like tuples, but they're not, is what we're saying.
Yeah, well, it's not tuples. They're not the same. They're just using the same symbols. If you
Yeah.
go really technical about it, but you can certainly think of it like that. And this whole plus ID. The important thing here to realize, and that's something they don't really tell you, is that these spaces here are what you would call an apply operator.
An apply
So,
operator.
like they are function application. That's what they mean. That's what it means when you have two things in a pure functional language with a space between them. It's saying apply the second thing to the first thing. So what we do here is we just apply these arguments to this function, and then at some point we get a result. Okay, having said that, I will go more in detail for this. This will click at some point, but we're gonna take it slow.
Yeah.
What will this evaluate to?
Ooh. So we got absolute value, which takes a integer, returns an integer, and val, which is just an integer itself. So doesn't that just evaluate to integer? We know that concretely because of the types.
Well, the thing is, moment please, someone's knocking away.
All right. We don't know. We don't know what it is. Ooh.
Sorry, someone came in. So we don't know what this will evaluate to, because we cannot look into value.
Mm. But
And
couldn't
actually,
if val is just an int, like couldn't you just put an int into like absolute and then like you get out an int? Funk.
we can even do it like this, when we know nothing about function,
Yeah.
how it's implemented, and we know nothing about value. So we have no idea what this evaluates to.
But why can't that just be int? Like why couldn't that just be int on the right hand side?
Because int is not a value. That's
Int
the difference between
not a value. Okay,
like
it's a type.
saying 5 plus 7 is not int. We can say that the type here is going to be int.
Yeah. But we
And
don't
this
know
is
what
the
its value
important
is. I see.
So what we have done now is we have done some calculations with func and val to say, oh, this type is int. And you might wonder, why is that useful? Well, what we can do is something like bool.
Okay.
Do we know what this evaluates to?
Is that even possible? Like, can you put val into func like that?
No.
So isn't that like an error or something?
This will give you an error.
An error. Don't like that.
Won't work. The problem here is you're trying to put a boolean into an int and they don't fit. They don't have the same shape.
Don't have the same shape. While they're both types, they're different types altogether.
Yeah.
Like we've defined them as two separate things. But in this case, we're trying to fit them together, and it's like, no worky.
Precisely. To really sort of... but the nice thing here is we know nothing about the implementation of val. We know nothing about the implementation of func. We do know that this expression is invalid.
Right.
In a sense, this is a really powerful system, because what happens in practice is that value is not just some bool, it's user input.
Yeah.
And with an integer, it's even worse.
So we've asked like a
So-
user, like, hey, like, do you want to turn the lights off or on? And
Precisely.
like val is like the representation of like the switch on our wall. And then func, but func is like, let's say that's like our absolute number function. And it's like you can't put a light switch if it's on or off into the absolute value function, because that doesn't make any sense.
Yeah. So if we go back to the int example, we have no way of knowing what this will evaluate to.
Yeah.
But we do know that it has type int.
I think some good intuition here is just like when you get like an error like this in the context of programming, it's like I like thinking of it as like you asked me, do I like what do I want for dinner? And I said, and I respond with
Yes.
the tea in China is dry today. And it's just like
Exactly.
that does not compute because that was not any of the remotely possible food options that we could have had for dinner.
Precisely. It
Yeah.
will just like, what am I supposed to do? Like people will, when you tell them that, people will be like, "Oh, what?
Yeah,
And
like
if you tell
your
that the
brain
computer,
short
it will be
circuits.
like, I'm gonna just crash.
Yeah,
I'm
right.
gonna
It crashes.
Give you
Yeah.
some errors now.
Yeah, we
Every day.
luckily have error handlers in our brain to adjust accordingly
Yeah.
when that happens, and then we trigger the "this guy's crazy" like line of thinking. Something seriously wrong with this
Yeah.
person.
In computers, we have a really, really fun other option that might happen.
Hmm.
They might just go with it. They might
yes.
just accept your nonsensical answer and start interpreting it in whatever way they seem most logical.
Right.
This is the
That's like it's like talking to a gullible friend where they think that they're always like wrong or they don't like quite understand, and it's like,
oh, I'm gonna get China for dinner now.
yeah,
Oh,
okay, we're gonna go
that's not-
Chinese, right? That's what you said. That's pretty
example.
good. That's pretty good.
Or like, for example, if you ask me what's your phone number, and I reply
Mm-hmm.
with potato,
Yeah.
you might find some way to convert potato into a phone number and just assume that is my phone number.
Draw me an image of
Which
a
is,
potato turning into a phone number. Let's see what ChatGPT comes up with.
It would have been great if you actually spelled potato correctly.
I
but
completely
digress.
fucked it up.
It was
I
still
never
there.
claimed to be good at writing English. I never claimed to be good at math. I just know a couple of things about programming. That's all.
So what we've done here is what I would like to call the type game.
Mm-hmm.
So I give you some types.
Shit. Totally did it.
That's horrible.
Oh my god. So this is
Why?
wrong.
Why does
We
this
know
exist?
we know that this is wrong, like in our core being. We don't want this. This is a lesson in
No.
like why we're talking about these things, because we don't want no potato phone number.
Yeah, it's officially the worst.
Yeah.
But my point being, this type game
Mm-hmm.
is really important.
Yeah, as we can see, we don't want our potatoes turning into phone numbers.
Yeah.
Right. So how do we address this? Where do we go from here? Now that we know that this is not what we want, but
Yeah.
we want to build more complicated things, because right now we've just
Yeah.
talked about really simple things that it's like, okay, great, like
Yeah.
you can do a little bit of stuff, but how
So-
do we expand?
To sort of build on this, and I think you might have to reload the page,
Why is that? Cannot see.
or I do, because the image is not showing up. On
Oh, I'll
my
just move it. I'll move it over to the side. Move our potato phone. So it's out of the way.
end. Oh, it's showing up now.
Oh, okay. I'll move it back. I think it's funny. You can work around it. Or on top of it. Who knows?
Guess we'll find out.
Yeah.
So that's not what I wanted. Let's look at plus again. Which is type.
Plus int takes 2 ints, returns an int. Kamu?
Conv.
Convert?
Yeah.
Okay, sweet. So we got convert, which takes boolean, returns an int, and then val, which is just bool.
Why doesn't? Bool. Yeah. Can you write me an expression?
Expression that does what?
I would like something of type int, please.
Something of type int. So it's an expression that the thing that comes out is an int.
Can you, given these functions, can you give me the simplest thing that will give me an int?
Could I do? Okay, I could just convert a val, put val into conv, and then wouldn't that give me an int?
Exactly.
Cool.
Do you think this would be a if our function gives us these inputs and demands this output? Do you think this would be a reasonable implementation?
Wasn't that just the definition of the
or definition? Same thing.
Looks like it does the thing. Looks like that should work.
It does. I have a small problem with this. I am giving you a function and you're not even using it.
Yeah, because in order to get that one to work, you would need like con val, or you would say plus con val in order to get that one to return an int. And I'm like grouping those two con vals because I know that that's how you get an int. Because if I would just say val by itself, that's just a bool. So I need something that ends up being an int, which conv is like the simplest one. And so originally said con val, but then combining those two in this monstrosity.
Exactly.
Yeah.
Note how you need the brackets here to basically say, oh, these things should belong together.
Yeah.
And this is a nice thing. This is another version of the type game. And this is actually the version of the type game that you often play when you do programming. You're saying, oh, I have all this information. Like I know how long something is. I know how big something is. I know how heavy something is. And then I want to know something about that. Like how long does it take to fall? How long does it take to fall down? And then you take your information that you have and you process it in some way in order to get your desired outcome.
Right.
And this way you can do some really neat things.
Well, it's already starting to look more complicated.
we're gonna go back to our plus and val example. What is the type of this thing?
We got plus int, and then that is invalid because we only have one int. Or no. Oh, ha. I see. So we're only putting in one int, but because plus needs another int before it can do the return value, that means that we're just going to get that tail end. So it returns an int function, I guess, that takes an int and then returns an int.
Exactly.
Because we're putting something in the first slot of plus.
we call this partial application. So that's basically saying, hey, if we have our plus function, what we can do, we can give in a single input, and we get our output.
Mm-hmm.
So the thing about this, if we were to write in the brackets as well, there would be brackets around here. This probably. In the same way that if you have something like to evaluate that, you actually have some brackets here. Does this make sense? It's on the right of your...
That makes sense.
Right a bit.
Oh, I see. So we got
Sorry.
4 and 5 grouped together.
4 plus 5 plus 6.
Plus 6, yeah.
And then plus 6. However, this is left associative. The implication operator, or like the arrow, is right associative.
Mm-hmm.
So that means if we write it without the blue brackets, then we actually mean these blue brackets. So it doesn't matter if we place these brackets here. What would matter is if we did this. So now we've changed the meaning. Our plus function no longer takes two numbers.
It takes a function that takes a number and returns a number. Ah, okay.
Exactly. This is an important difference. One of the most confusing things to people is this right-handed associativity. So you should know you can always put the brackets on the right. Also means that if you want to have a function as input, you should put the brackets around your integers. That also explains why, if we look at this again, y or integer with a plus, we now say, hey, we have a function that takes some integer and returns another function.
Right.
So,
which is more or less effectively what we did on the bottom there with like plus int returns. But that wasn't the explicit meaning in the original one? Like when you originally wrote plus without the brackets? Or were those brackets really kind of there? They were just hidden?
Yeah, so these brackets, I'm going to make them. Like, these brackets, I'm going to make them blue. These are here, but you don't write them.
Okay.
The reason you don't write them is if you have something that takes 4 arguments, you have something that ends in this.
Yeah.
Which no one wants.
Yeah. So it's a bit of a shorthand to remove those, but like as we see that, if there's no brackets, we can kind of assume that that's the...
In the same way that if we write some like function, plus 7 or whatever, you also get the brackets here.
Because that's because of left associativity with like math.
You do the left side first.
But in our type world, we have right associativity.
Yeah, for this operator.
Yeah. Does that have a name? The
And
arrow? I'm calling it arrow. Does that have like an
it's called implication.
implication? Int
Yeah.
implicates another int. Is that how you
Yeah.
would say it?
Int implies into int.
Oh, okay.
You
That's
would pronounce it as like usually you say int to int.
int to
Like
int.
I would pronounce this as int to int to int.
Which maybe kind of makes sense too. Maybe. I like arrow. Maybe I'll keep calling it arrow for now.
Yeah. int arrow int also works.
Yeah.
I will probably use this inconsistently.
Yeah. Right.
But that also would explain why. Also, I just realized I made a mistake. It shouldn't have been int. It should have been val. A nice thing to know here is that now we're back to our original example where our type is just int. But what we actually do here is we take this apply operator, which is here, which takes this thing and basically computes them together.
Mm-hmm.
The type of this thing we've just seen is a then on the second step, we take this part and take this together. And we say, oh, we give some integer to this thing and we produce, finally, a int.
Mm-hmm.
Because this thing has type int.
Plus val. So we're first doing that, and then we take that, the return from that, and then
The weird thing is in these, if you think about it like this, you have no functions that take more than one argument. They don't exist.
So that's always true in the way that we're writing types right now. Is like there's a function only ever takes one argument.
Precisely. And then a function where you would normally say like plus takes two arguments. That is logical. But you can also say plus is a function that takes one argument and gives us another function, which in turn takes one argument, which then gives us an actual value.
Which is pretty ludicrous to think, because do you see the JavaScript example that I have over there? On the side?
Yes.
Maybe. It's like pretty ludicrous to think if you were to write this in JavaScript, you would kind of need to follow this syntax if you wanted to achieve how you were just writing it there. Like it's like it's like insane. There's just so much. You would be writing function forever.
Yeah.
And then return function, return like the other function call. Like But we're defining something completely different here.
Yeah. It turns out this is actually really useful. To show that, I'm going to give you one of the most used functions in all of functional programming. But first, I will have to introduce a new data type. What is the type of this thing?
Is that a list? We call that a list.
That's a list of int.
Oh yeah, right. The type that's in there.
The type is a list of int. This is also commonly written as just a list of int in the types. Those are two different notations. You can just put list in front of it and then be like, hey, or you can do it in brackets. I like this representation better because it looks the same as actual lists.
Mm. Makes sense. Got your ints
So
inside
now
of your list.
what we can do is we can have a function called map, and that has a certain type. It will take an int arrow int, and it will take a list of int, and it will produce as a result a list of int.
So map takes a function that takes an int, returns an int, and then then we got the arrow. It has a list. Oh, right. Okay. So right, we're looking at the inner part first, and in our.
So
how do I undo?
Let's do this with an example. We're going to take our absolute function from before, and then we're going to give a list with what does this evaluate to?
Map of absolute over the list of -5, 2, 3, -2. So going through each one of those, 5 -5 becomes 5, 2 becomes 2, 3 is 3, -2 becomes 2, +2.
Exactly. This is what the map function does. It takes in some function and it applies it to every single element of your list. Nice and simple, but looking at the types, it can be a bit confusing.
Yeah.
So you have this like list of int to list of int, which makes sense because you have some input list and some output list. And then you have your operation.
Yeah, I think when I look at the syntax with arrows, like I think my mind originally would think of like, kind of like, and there is some truth to this, but it's like a data flow. Like we somehow like an int flows into an int, and then that grouping flows into the array, and then that array flows into like the other array.
Here, it might actually make sense to add in the extra brackets.
Yeah. I think when you start doing that, now that starts to make a little bit more sense. Like grouping it, like showing that type of like visual is helpful.
Because now map is a function that takes itself a function, and what it will do, like absolute, it will give us a function that will take any list and convert it into a list of the same type. Do note that these two lists do not have to be the same. In this case, they aren't. Like the things that are of this type do not have to be the same.
Yeah.
Just the types have to be the same.
Just the types, yeah.
And this can help you sort of slowly understand this whole type system business. That brings us back to this like nice partial application.
Oh, I do have a question. So, from my understanding of map from programming, I know that the list that comes in is always going to be equal to the length of the list that comes out. But in our types, we don't say anything about the length, because we've moved away from like expressing like a list of things as a tuple to now like a list of things as like this like unbounded like size. So in our type system, can we declare at all? Like, do we have any guarantees that that's going to hold true?
Because this is one of those things where if we want to retain this guarantee that we can say something useful about this without knowing the actual values of what is passed in. So if we take a simple function like string repeat,
Hmm.
then we have as input an integer and then a list of characters, some string, and then our output is another string. But the length of that string is completely dependent on what our integer is.
Mm.
So in that sense, you can no longer say anything about how this string, like the size of this string, because you need to know the exact implementation details. And the whole point of types is that if we make this type system happy, we can basically know that we use our program in a valid way.
Hmm. But
So
it is like we are taking like the trade-off here, because it's like we can't like kind of when we introduce the list here, we can no longer kind of uh, be like explicit over what's coming in, like absolutely explicit about what's coming in versus what's coming out, because it's like we've lost the idea of like length. Is that fair to say?
yeah, but we've also already lost the idea of value. If we do int to int, we can also no longer be exactly sure about
Yeah, I
the
guess that.
range that
Yeah,
this
right. Yeah,
integer can be
right.
in.
Fair. That's
So
reasonable.
we already lost this battle.
Yeah, right.
The whole point was losing this battle.
Yeah. Very cool. Very cool.
So here we have a nice example of partial application. Can you give me what this evaluates to?
Map plus 4. So plus, where do we have plus defined? I got it up here. So plus is we give it an int and then it returns a function that can take an int and give it then return an int. So we're passing 4 there, and so we're going to go through a list, and I'm going to say plus 4 4, which is 8, plus 4 2, which is 6, plus 4 3, which is 7.
Exactly. Being able to do partial application here and to not have to define a special function called +4 is bloody useful, as you might be able to see. And this way of defining stuff and allowing you to do this partial application is a really important aspect of this whole programming business.
Mm-hmm.
It makes you, I should have put it, it makes you really think about programs more as in types than in the values.
Right.
So, as an example, we can have a function like this. It's going to be a bit of a long one.
Ooh. String, bool, int. String, bool, bool.
Right.
It's a weird looking one.
So our function f will have the following type. It might be nice if you can get that all on screen at the
Can I
same time.
zoom out? Yeah, there you go. Just a little bit. Cool.
Yeah, nice. So now my question is, like, what we're going to do is we're going to define we're gonna a implementation of this function.
Mm-hmm.
So the first thing that I would like to know, how many arguments do we like? What is the return type? Let's start with that.
Return type is an int, the one that's all the way on the right.
Exactly, the return type. Can you tell me how many arguments we have?
How many arguments? Well, we've grouped together string bool int as one, and we've grouped together string bool, and then we have bool. So argument count 3.
Why are you being annoying? Would you not work properly drawing thing? I'm just gonna stick with it. Why I lift?
I really need like a tablet that I can like draw, because I have like a.
I
Oh,
have
like a
one.
wheel
They're
mouse.
awesome.
Yeah, is that what you're using right now?
Yeah.
Oh, that's so nice. What
I'm
brand?
not using a mouse.
What brand is it?
Wacom.
Yeah, okay.
Because
Cool.
yeah. So these are our arguments. So the first thing we're gonna do is we're gonna say f, and we're gonna use the style of the plus we had earlier. So we say the name of a function, which is f, and then we're gonna name the inputs. So they come here, and then we say is, and then we use our inputs to produce something of type return. So we can call them, let's call them G. So this one is going to be G. I'm going to call it H. This one's going to be H. And let's call the last one, let's call it B for bool. So we have our inputs of our function, G, H, and B. Now the question is, how can we use these functions and values and apply them to each other to get something of type int?
How can we apply those to each other so that you can get something of type int? Are you talking about like what would the implementation of the function look like?
I messed something up. I'm going to switch these around real quick.
Bool to string. String bool int. What would that even look like?
So what we want is something of type int.
Right. But we got this like hodgepodge of other functions that do things.
Yeah. So if we are looking at all these functions.
Yeah.
Which one is best to use if you want to end up with an int?
Oh, okay. Yeah. So we want G, because G will eventually return it, and none of the other ones return it int.
Yeah.
Cool.
So we're going to do G, and we're going to do some defensive programming. We're going to already put in the brackets.
Okay. So if we want to ultimately end up with an int, and we're starting off with G, we know that we now need a string and a bool to go into those brackets so that we can fill in those slots.
Yeah.
Get in those slots. So how do I get a string out of this? Well, I know H can return a string, and but H expects a bool, and so what do we need to give H? We need to give it B in order to get bool. And then in
And
order
what
to
do
get,
we need here?
we could just put B there.
Exactly.
Very
And
fun.
then if we clean this up, we get
Very good. We love it
what
when
we've
everything
just done
comes together.
is we have looked at the type of our desired function. And purely by looking at this type, we have figured out the implementation.
Yeah, that's true.
And this is what you're doing 90% of the time when you're doing functional programming. So you're not thinking about, oh, what value should I do? What operations should I do? The first thing you do is you say, oh, I have these inputs. I know that I will need them to create this output. Now I just need to hook them together.
Mm.
And this hooking together can often be done by simply looking at what you have provided.
Right.
Also note that there are some, like, usually functions like map are available everywhere. So you can always use something of type of map.
Mm-hmm.
The nice thing here is that what you can do is often just getting this type checker to work already sort of forces you into a very limited set of possible solutions.
Mm-hmm.
Where with more classical programming like JavaScript or something, you basically get this entire universe of possible things, and then you need to somehow change the data in such a form that you get your desired result.
I got a question. So we have
Yes.
G, H, and B in here. What if we also introduced like C as a parameter, and C was of type bool? Like we wouldn't necessarily know explicitly to use like B or C in our slot
Yes.
where we accept bool. So how does that relate to what you're showing here?
So how the lovely example I was about to get into.
Oh, okay, sweet.
The biggest thing is this is only for these kind of cases where you have two possible ways of doing something.
Mm-hmm.
You will get your desired result. In the same way, if we look at our plus function from earlier, so we have a type. So when we define plus, we have two inputs, an x and a y, and that needs to be something of x. So we have our x or y and our result. A implementation of this could be this.
Right.
This makes our type system very happy.
Mm-hmm.
However, there's something kind of weird. Because right now we're not using any of our inputs. What we could do is we could define this as x plus x.
Mm-hmm.
This would also make our type system very happy.
Right.
The big problem with this is we're not even using y. So when doing this and when you're looking at this, you most logically would come out to something like this. If you know, hey, I need to use the plus operator somewhere, I have an x and a y, maybe use them. In some cases, you might need to swap them around. But this is usually where, by giving this type, you basically get these guardrails which really focus you on where do I actually need to know if I should use X or Y.
So
Or
it's
with
like
the example.
guardrails. It's not like telling you explicitly what to do, but it's like at
No,
the very least like making sure that when you're connecting things together, it's like you're selecting one of like few options versus like everything.
yes. And there's an added benefit to this. If you are using this type system for everything, like we've been doing right now,
Mm-hmm.
then for any program you can write, you basically have two possible options. All the types can fit together nicely, and we do not have something where we try to put a boolean into an int, for example. So every thing can fit together nicely, or it cannot.
Right.
If it doesn't fit together, it's no point running the program because you're doing something stupid or there's something weird. It's going to complain. It's going to give you an error.
Mm-hmm.
Another nice thing, if you are implementing this properly and all these types work out, you can statically guarantee that you will not have any runtime errors. So that means that you are unable to express a operation that will make the computer think, I don't know what this means. In the same example, that like, what do you want to have for dinner? Uh, Flamingos are pink birds.
Yeah.
That makes no sense. Then the computer would be like, hey,
It almost kind of
I
the
have no idea.
the thought that comes to mind is it almost kind of feels a little bit like types are a little bit like parenting. It's like you got like parents are there to kind of guide, but at the end of the day, they're letting their kids decide like how do you actually want to implement this.
Yeah,
And like that actual implementation could be a crazy optimization. Like you could be doing like crazy like bit flips and whatever to make it achieve, but it doesn't matter as long as the types are being like
yeah,
fulfilled.
yeah. That's another thing about this whole type theory stuff and this like functional programming. You can do ridiculous optimization
Right. Yeah.
because there's one important aspect that I haven't really talked about yet about how this incorporates into actual programming languages, and it has to do with that using such a pure functional programming language. Well, it's sort of in the name. They are what you call pure.
Pure.
So the definition of a pure function is a function that does not have side effects.
Mm-hmm.
Which brings us to the next question: what is a side effect? So a side effect is anything that a function does which isn't encapsulated in what it returns.
One more time. A side effect is anything that it does that is not captured in the return. Okay.
Yeah. So a plus function returns some value, namely x plus y.
Mm-hmm.
However, if we do this in something like JavaScript, we can return x plus y, but in the meanwhile, we can change some internal variable somewhere.
Mm-hmm.
And changing this internal variable is what is called a side effect, because you do not see by looking at the return that this is changed. And the nice thing about this whole purity is that this will also guarantee that if you have the same inputs to a function, you will always have the same outputs.
Mm-hmm.
The reason why this is nice is that also means that because everything is encapsulated in the return type, you will never have a case where you copy a function and basically use it a second time somewhere completely different in your program, and it will break your existing implementation. While if you have these like side effects, you can definitely have some like unintended side effects. For example, you might have some programs use an internal counter to count how many times it has done a certain operation, and it might use that to make certain optimization decisions.
Right.
However, if you then copy that code and put it somewhere earlier in your program, if you do
Oh,
not take care to reset this counter, that means that the second time it goes to the code, which you haven't changed, you just copied it. Now this internal counter has like a really high value, and your optimization will start making really weird choices. And these
you
are
talking about this is like
horrible.
so triggering for me because literally yesterday I had to refactor this library, this Go library, because the way that they had implemented it was using using side effects that were happening on like the global scope, and they were using the init function, which is like a function that when the module is loaded, it runs. It's like essentially like global scope, like just initially being run. And so they were setting state and keeping state there. And so I ran into problems using their library because a part of what they were doing was reading for the existence of an environment variable. But there's different settings in which I'm using this application, and like the environment is like changing in these different things. And I wanted that value to come from like a configuration file and not just an environment variable. And so in order to achieve that, I had to completely refactor the way that they were handling that state, because it becomes a very leaky design to have those side effects. And it's painful because it doesn't give you control over your code anymore. Like you're kind of at the whim of however that person decided how side effects are handled.
Yeah. So the downside of that is basically whenever you have some code, you will always be forced to look at all of their code in order to use that application if you want to be certain that using this won't mess anything up.
Right.
Because in the worst case, they might use a global variable that you are also using for something completely different, which can create a whole another difficult type of issue, which you might not like. These are really difficult to find because you need to go through every single bit of code.
Yeah.
However, with this like these pure functional types, you are assured that everything a function does is contained in the arguments that you give the function and how the function returns.
I have
So you can completely safely copy a function somewhere else, and you do not have to worry about it messing with anything.
that is like incredibly powerful. The more that I study writing programming, and the more that I feel that feeling of being able to copy around my code without any side effects affecting like my ability to like write more and more code on top of it, like you feel yourself writing code so much faster. Like the actual lines of code don't really matter anymore because it's just you're writing those lines of code to make that like building block that you can later use. And
Yeah, like
what I was gonna ask is why do people use global state? Like, and this is more of an opinion question. Like, is it easier to conceptualize? Is it something that is just taught? Like, do you have any like thoughts about that?
The reason historically is very clear. It's performance.
Performance.
If you look at how a CPU actually works, it has this memory which stores variables, and you can basically access them and change them from anywhere. So this is if you're working in like a lower language level programming language like C, you can use this stuff, and you can even do stuff like pointer arithmetic. So it makes no like it's in that sense it's a bit weird to have a language that allows you to have these variables and you can like change them anywhere. You can have these like whole scoping rules and everything, where you then say like no, every function may only use the variables that it is explicitly given.
Right. We got it. We got a
Because then
question.
another
Question from the chat. When are side effects acceptable?
when are side effects acceptable?
When are they
That's a good
acceptable?
question.
That is a good question.
So it sort of depends on who you ask and what your goal is.
Mm.
Because if you are working on code that needs to be used by multiple people for a really long time, having like undocumented side effects or like weird side effects is a recipe for like really buggy problems that are really hard to diagnose later.
Yeah, and there are the side effects that are inescapable, like I/O. Like if you're interfacing with the
Yes.
real world, it's like you can't encapsulate what's going to happen when you're interfacing with the real world. Like
Well, that's not exactly true. You can
I guess
encapsulate that.
your function can describe what it's emitting. Ah, That's interesting.
Like there's this whole IO. Most like a lot of functional programming languages make exceptions for printing stuff to the console,
Okay.
or at least they sort of automatically convert your code into a pure representation that can handle this, which is not exactly the same. There's some subtleties there, but then it's fine. There are also cases where, in general, having these side effects is completely acceptable because you might work on a really specific piece of code, or you might have documented it properly. So you need this. There's a lot of situations where you need it simply as a performance trick.
Yeah, any
Which
type
is a
of
very
shared resource like concurrent programming. Like
yeah.
if you're dealing with
If you're
locks and stuff like that, like
yeah, then like some programs you I wouldn't say have to because there's almost always a functional pure way of doing it differently, but it can be fine to do this.
right. Yeah,
But I think the
it's a
most
matter of what limitations you're dealing with. And if you're in a
yeah
research laboratory, that's very different than if you need to write code for like a embedded device that's going to be like you're going to make 1 billion of those and ship them across the world. Like it's a completely different application of programming.
yeah, and the thing here is it's mostly a maintainability thing, and that's in general where the biggest difference between these pure functional programming languages and the more like classical imperative programming languages is if you look at a graph where you have effort on one axis and time. If I can time on the other. If you look at a normal imperative project, you're going to do quite a bit of work on the start.
Mm-hmm.
And then this will fall off, and then you will get to some floor of maintaining an application.
Right.
And this is, for example, a website or stuff like that, where you need to make sort of the main body of the website like, hey, it needs to have like an about page and a hello page, and then people will ask like, hey, could you add this page, or I would like a button here, or can you have an overview?
Mm-hmm.
And those are smaller changes. You don't have to write an entirely new website, you just change the small bit.
Right.
And what functional programming tends to be is this. I should use a different color. Functional programming tends to do this. You can spend quite a lot of time on figuring out the right monads to use and the right functions, etc. However, after you've gotten a reasonable model, you basically have your type system that will safeguard you against a lot of, how should I put it? There's a lot of errors that you can get using imperative programming, like these. Oh, you use a variable somewhere, you can just copy the code or whatever, which you don't have to worry about with functional programming because the type checker will find them for you.
Right. How to, in a healthy way, deal with side effects when you can't avoid color functions, for example, how to manage them? I'm not entirely sure on that question.
Yeah, I don't know how to parse that.
Well, our minds are geared for like a certain type, and we just received the type that we were not familiar with. It is English though. We did parse some of that. I think you said it great. It's
I
like
mainly don't know what colored functions are.
colored functions. I think is generally there's a famous blog post, I believe, is like the etymology of this in programming, where someone was trying to explain the problematic side effects of like modern async await syntax in code, where once you start adding it somewhere inside your program, like the parent, like the callers now have to adopt this or handle that concretely. Versus in my experience with Go, it's like you don't have the colored function problem as it relates to concurrency, because you can just kick off a concurrent Go routine anywhere, and the caller doesn't have to have any knowledge that that's what you're doing. So I think this is in reference to like if you have side effects somewhere deep in like your code that you've just added, what about like the parent functions that are like calling into those functions that have side effects? Like, how do you manage that? And like maybe an example is like there's a function that deals with concurrency or parallelism, but that's like a function that gets called like 1,000 times throughout your program. And now it's like you now have this like function that has side effects that's used widely throughout your application. Like, is that a problem? Is that a problematic function to have? And I think probably the best guidance that I can give around that is just kind of being as explicit as possible, like documenting side effects, like because in reality, all that types are communicating what's happening with the function to the person that's about to use them, or also the code that's implementing the function. It's just trying to describe what it is. So oftentimes, like, just a really well-written description of what a function is, if you can't fully address the scope of what a function is going to do, is pretty good. It gets you pretty far. It's not perfect, but like we've already established, like neither is our beautiful type system here. We're still losing information in the process of describing things as we are, but it's still pretty good.
You can see types as a sort of enforced documentation.
Yeah. And they work beautifully if you have a good type system.
Yes, that is a prerequisite
requirement. Cool. All right.
And
keep going.
Yeah, like having this be consistent is a really important part in that, because you need to be able to trust it.
Yeah.
Because if you have something like JavaScript where you have all these side effects and whatever, you will never be sure that if you look at someone's code, even if they say they won't have side effects, do you trust them?
Yeah.
Are you really sure?
Are you really sure? No, I never can be.
You never can be. Well, yeah. If I give you some Haskell function and you say it has no side effects, and say, yeah, duh, it cannot have side effects. You cannot express something with side effects in this language.
Right, yeah.
Which gives you a bunch of like these positive attributes about your program, which make, in general, like editing, maintaining, and refactoring it so much more pleasant, because the type checker will help you. Another thing that I really haven't touched on yet is specifying these types can tell you something about a function before you've actually written it. The nice thing about that is that your error messages greatly improve if you give a function before you start implementing it.
Hmm.
Because if I do, for example, if you look at the plus function here, if I do something like if I do something like this, currently the type would be a tuple of int uh, this the type of what I've just written, because I made it a tuple for some reason, and then I've taken the plus operator and applied it to only one argument, again giving us a partial function. And then what you will see is the error message that you will get will look like it will say like, hey, I cannot unify int to int with int to int graph to this is the error that you will get if you top right a bit. If you move your
Oh, we're missing it.
it's like up here. Yeah. So it will basically say, hey, this is what you specified. But what we actually see is a function that takes two integers, namely your x and or y from earlier, and it will take that into some like weird tuple thing, and it will say, hey, these do not match. It says like, hey, it will say, I expected an int here and I got this thing instead.
Right.
Which, if you hadn't put this type here, it would have just happily allowed you to do this. And then only later, when you try to use this value, it will be like, hey, your input to this thing is some like something of this shape that we had here before. And I don't know how to work with it. So in that sense, you by specifying this type explicitly, you can pinpoint the cause of your problem much more accurately. You should basically say, hey, this function should look like this, and then the compiler will give you an error when it says like, hey, this doesn't look like this. You made a mistake. And then you know, oh, I made a mistake in this function. Instead of if your mistake, if you don't explicitly do this, this value might travel like might travel to you through your program for a while, and then at some point it says like, hey, I cannot actually use this thing because I expect an integer here, and then you get some error, and then you would need to trace it all the way back through your program in order to get to where you were.
Yeah,
So
I
in that
don't
sense,
understand how people develop like that, where it's like you have some error related to a type, but now you have to like traverse the control flow graph to all the possible places where that could have come from. And there is a way to have like a debugger set up where that makes it easier and you can look at call stacks, but it's like dealing with that like day in, day out. It's just like that makes me hate programming. I don't like it. It's very demoralizing. Like types, learning how to use types and implement them in code, it's not just about like the talking to the computer. It's also about just like your own sanity and not feeling fucking crazy when you haven't looked at your code in a week and coming back to it and being like, okay, cool, this is where I left off.
Exactly. And being able to do this effectively and mess with these types can really help you a lot with programming, because it allows you to catch problems much more accurately than
Yeah.
otherwise. Although there's like, this is not a golden bullet.
Right.
You can
I believe the phrase is silver
still
bullet, but I don't know what they say where you're
silver
from.
bullet. Sorry, it's it's not a silver bullet.
It's not the golden bullet.
You know what I meant.
Yeah, I did. Yeah.
It's
Incorrect
it's not
type.
a silver bullet. Like you can still have like a plus function defined as just returning 2. Like doing this as our function, where we say, hey, this is 2, is still perfectly valid if you look at the types.
Which is interesting because I've recently kind of been interested in like I'm sure it has some name, but like definition, function definition first programming, where you define like the contract of what a function expects as input and output, and then you just like stub it out. You just like conceptualize, this is a function that I believe should exist because I need to transform this data into some other data. I just make it exist, and then I kind of do what you just did there, where I just put like return 2, like return something, and start to build out like maybe like what other data might this need to return, and expanding on that like basic idea of like this function needs to exist. These are the types. Now let me play with those types to mold this function into what it really should exist as. And I find it's a nice balance between thinking through like concretely what are these types, but then also going through, and it's kind of almost becomes like a little bit of test driven development too, where you're testing your function to make sure that it's returning and doing the things you expect to as you kind of understand this function more and more. I find that it's I can code much more quickly if I use this approach.
Yeah, I think that the whole nice thing about types is you effectively divide your writing a function up into 2 steps. First, getting the types to work, and second, getting the actual values correct. For example, sometimes you just need to give some value somewhere. Then it is not uncommon to just put like 42 there and go back later and see like, hey, how does this changing this value actually change my output, and then playing with that value till you get the right approach. Because you don't like, it's a very common thing where people spend 5-6 minutes thinking about if a Boolean should be true or false for a certain problem.
Yeah.
Well, just test it with true, test it with false,
Yeah.
see which one is correct, use that one. That doesn't take you 6 minutes.
I almost want my editor to have little flips and stuff, little number inputs where I can like just change a number like that, or maybe like with AI, like it'll automatically kind of like fill in like the possible values and just like automatically test your function for those types of things. That's really cool.
What unit tests do.
Yeah, exactly right. Yeah, just building unit tests are super helpful.
And
but
that's
what I don't like about
thing.
unit tests is that when it comes to like if my function's kind of still in flux and I'm still not quite sure what the definition should be, having written unit tests, like they'll just kind of like instantly break and not be all that useful. So when I'm doing an initial pass over my code to write it, I write like small unit tests here and there to kind of like enforce my to kind of check my expectations about what's going on here and kind of give me a checkpoint. But very quickly, these small unit tests kind of go to the wayside as I'm like still thinking through what are all the functions that exist here and how do they relate to each other, because the actual definitions might change drastically.
Well, another nice thing is if you look, for example, at Haskell, it has also a interpreter, so you can.
That is nice. I do like that. Yeah.
Functions on the fly and try them out and see if they work.
Yeah.
But for most cases, you can just sort of try them and see where they go wrong, and then based on that, sort of change the values or just binary search your way to the solution
Yeah, right.
is often so much more efficient than actually thinking about them.
Yeah.
Often that also causes issues later on where you didn't account for edge case X or whatever.
Yeah.
Like, I'm not trying to discourage.
It's kind of the thing that comes to
Thinking
mind
about
is like the inverse square root function that like was implemented in Doom.
Yeah.
Fast inverse square root or something like that, and it
Yeah.
was like an approximation, but it just like there's no way that any human could have come up with like that the formula for that approximation. It was just like such an incantation.
How do you? A human has come up with this. What are you talking about?
I know it's brilliant human minds. All right, so where are we with our explanation of types? Are there more things that we would like to discuss in this general type sense, or do we have enough built to kind of go to Elm?
There's one thing I'd like to do before we go to Elm.
Cool.
And that goes back to something that we lightly touched on at the beginning. And that has to do with something like we remember the tuples, right? The string in pairs. What we can do is we can define a function. Which we define like so. What would be the type of this function?
Well, we don't know. We have no intuition around what X or Y could be because they're not like, there's no like addition of 3 or something like that that would imply that it's, that we could infer that it is an integer. So, X and Y can be any type. Both of them could be the same type. They could be different types. And it returns a tuple of those two types combined together.
So what we can do for the type is we can call X, we can call that A.
Mm-hmm.
And in this case, a lowercase a represents any type. Then for Y, what we can do is basically we look, hey, how is this somewhat restricted? And we can look at, hey, should it be a string? Should this be a integer? Should it be a Boolean? Should it be some function? But we can also we also need to know the other things. Does it need to be the same as X, for example? Because sometimes you have a constraint where it doesn't really matter what X and Y are, but they do need to be the same. In this case, does Y need to be the same as X?
No, there's nothing that requires it to be. Because a tuple could just have two different types.
B. Then our result would be an A, comma B. What we've now done is we've taken this function and we've computed its most general type.
Mm-hmm.
What we could also do is we could give it this type. If we, I shouldn't write arrows. If we give it this type, what we basically say is, hey, only use back on integers. Even though in this case it can be You've been adding a lot of images, so it no longer likes.
Oh no, is it too big?
Yeah.
We'll get rid of some. Oh, it's too big. What do you mean
Yep.
it's too big?
Couldn't say to the backend database again. It seems to be
God,
being
this looking at this, I want to write my own. This is like this should not be. I don't know what the hell is going
Yeah.
on here. Like Excalibur has been around for a while. Do I need to pay them money? Ugh.
I don't know, man.
Ugh.
We should have figured this out before we started streaming.
It's fine. It's fine. You can save like an SVG of this or something. I hope. Save to disk. Save to desktop. Yeah, I can save it locally. So I guess we'll just do that.
No, it will still allow me to do this thing. Okay.
Oh my god.
Anyway. So, anyway, we have made these types. So we can give this a more general implementation. It keeps complaining.
It does keep complaining.
Yeah, I don't think it allows me to send you data anymore.
Oh no. I'm trying to remove some images.
Can we just open a new one?
Could just open a new one.
That would work fine on my end.
Oh my god. New one? How do we...
If you can send me a link, then I drink a bit of water.
Just go to... Okay, then we add, start session, copy link, share link.
There we go.
There you go.
And that's all backed on the images this time.
Yeah. Well, now I know what I want to code, so I want to add that to the chat app. The ability to just like drop it into like a whiteboard. That'd be pretty sick.
That would be pretty sick.
And then we can move like the chat like over to the side as like we're like pulling up the whiteboard to explain something. That'd be pretty cool.
So again, we can use these two different variants to limit the scope. So this one is most general, and this one is basically limiting this to just being integers.
Mm-hmm. Which is okay. All three of those are like all like okay to like express in the way that they are.
Yeah.
Yeah.
So now our type game changes a bit. So if we say we have a value of an int, What is the type of this
So we got pack,
small expression?
an int. Okay, so it's not fully applied. So we have partial application of val, and we are going to return
Well, partial application of pack.
or a pack, yeah. We're going to turn b into a comma b. Would we still? Oh no, because we know it's an. Oh no. We had a b going into int comma b. Because we know that a is now an int, but we still don't know what b is.
Precisely.
So we've been able to do something. We know something
Yes.
about this.
And the most notable thing is that here you can no longer be like, oh, the first thing matches the first thing. We're just going to replace them and look at whatever we have on the rest for the rest. Now we need to do something more. More. We need to do something more. Because we also need to replace all our instances of A with whatever we plug in here. So that basically means whenever we plug in A on one end, we know that we also must plug it into the other end. It also means that if we want to take a func, which should have the type
func int into bool into int bool func xy.
if we say pack by y, for example, looking at this, we know that the result of this thing should be int comma bool. And our pack should be of the right type. The challenging thing here is when we try to apply this, we first look at this section, which will give us a type, as we've seen before.
Right.
B, then.
But bool. Why? Yeah, okay, yeah. Because now it's a bool.
B. And then our total type here would be
bool comma bool. Which is a discrepancy from the above line.
So it will tell you the error is here. It will tell you that this thing and this thing do not match up.
Yeah.
However, what it should be telling you is that this thing is the wrong input. That is for you to figure out. So in this case, blaming which part of the code is the problem is kind of difficult. So on the one end, we say, hey, these two don't match up. You could also say, hey, this y does not match up with the type that we desire, because this should be an int. So basically the question is, if we we have two scenarios. Oh god, that's not what I wanted. How to use this drawing application.
Can you undo? Oh, there is in the bottom corner.
We can say either this thing, which has this type, does not match up with our result type, or we say this thing does not match up with an int to get a correct result type. Which error you get depends on what programming language and compiler you are using. These can be the hard things about messing with these types. Because it might, in this case, it's clear that the solution here should have just been that this is not a y, but this is an x. We want this to be an x and a y. And then our types match. Hooray.
Very good.
But if you make the small mistake here, you can get type errors in places you don't want. And this is one of the things that I'm researching how to fix. These
how to provide more helpful error messages.
Yes.
Yeah. And I did send you that I forget what it's called, but that one language that aims to kind of be provide like more helpful error messages. Like that was kind of like the whole goal of the language.
Yeah.
Built on Elixir, I believe.
So in that sense, it is
that's a hard problem because you don't know what someone's intention was. And you're trying to deduce what was the desired goal.
But this has given you, like, knowing that you can have these abstract A to B things. What you will also often see is if you define something like int to bool to int to bool, and you give something like you can give a function that in itself has something like that looks like pack, then what will happen is you will get your type where your like concrete type that you've specified does not match with some generic type that the programming language will infer.
Right.
Because what will actually happen is we've been playing this type game, giving you some expression and telling you, hey, what should this type be? However, the computer can do this for you. And actually, the computer is way better at playing this type game than any human can be.
Yeah.
Because how does a computer check that your type matches with the type that you've specified? Well, what it does, it just ignores the type completely. Then it tries to figure out, hey, what is the type of this? And then it will see if that can match with the type you specified.
I think the when I wrote a type inferencer in Haskell for my compilers class in college, which was very interesting. And you saying that reminded me of that like process of like how do you understand what type that you're dealing with? And it's like you gotta try to like fit in all the things together and like do they fit well? Like if so, it's like you're good. If not, like, oh, you got a problem here, bud. Like you're gonna have to fix this. It's not easy.
One of the nice things here is that the general, like, I think I'm getting a bit tired. I lost my sentence.
I was gonna recommend maybe we should hold off on the going on the Elm journey for another one, because I could get out and walk around while there's still a little bit of light left.
And that might actually be wise.
Yeah, I
But,
think we
this
have
is
a
the-
really solid. This is a really solid intro. I feel like I'm taking like the intro class to like programming languages like through this. Like this is very
Yeah.
nice. Oh, our whiteboard. Oh, that's so sad. Yeah, this is
But-
really good. This is really good foundation for introducing Elm, because I'm thinking about the elements of Elm that got me really excited when I was looking at it, and it's just such a really nice distillation of all of the things that exist in a type system like Haskell, but kind of like limited down for the scope of web applications. And it's like a very focused application of the type system, which is like very encouraging for me. Because there's also like Reason ML, which is built on OCaml, but it has the problem of it's still full-fledged like OCaml. And I think that maybe the direction of where functional programming needs to go is taking away those options, but still giving you like the vast amount of what you would be doing. Because if you're building a website, you're not reinventing the wheel. Like yes, there are a lot of really challenging problems there, but it's like, what? Yeah.
The main thing that I think sets Elm apart from something like OCaml or Haskell is that Elm has really strong tooling,
That's also true.
while OCaml is essentially a research language.
Yeah.
I mean, it's not really, but it's still sort of in that stage where it is used mostly by people who are very proficient in either other functional programming languages or in OCaml, because they've effectively stuck through it. Well, if you look at something like Elm, I can recommend most people Elm. I do a bit of this like type theory, like playing this type game stuff,
Mm-hmm.
because knowing this, what we've done today, in a more fundamental sense, sort of shifts your view from, oh, I need to compute this thing, to, oh, I need to make the types work.
Yeah.
Because we've been like using the functions called func and pack and whatever, which might not even have a proper implementation.
Mm-hmm.
But that does not reflect that we cannot work with them, or that we need to understand them first. No, we first need to make the types work. And then if we get an option to choose between two things to make the types work, then we go and think, oh, we should do this. We should actually not only pass this variable around, we should like increment it at this point, stuff like that.
Yeah.
And
Well,
that's
I think
second step.
what's interesting is like thinking through it. It's like initially we introduced the implementation of plus with like the normal like integer on the left, plus sign integer on the right, but then we defined that with plus xy, and like you can very clearly demonstrate the implementation of that with the more like canonical expression, canonical symbol of plus with the plus symbol. But then building on top of that, we're now at the point where we have like func xy, and then we actually wrote the implementation of func xy with pack xy, which is like what the desired thing was. And like what's really encouraging is seeing like all of these things kind of like combine together, and you can like grow in what it does, grow what your code does very succinctly is like the really motivating component here.
And I would like to emphasize, like, you can go much further with this.
Yeah.
As in, you can have types that, or functions that have types as input and produce other types, or you can have like types that return values, and you can like really abstract away from this whole principle. There's no reason this should only be types, or this could not be a function that also takes themselves types as input.
Mm-hmm.
You have the whole Haskell school where you basically say, hey, we do allow these like A and B things where it can be whatever, but we're going to limit them to some instances of some class, basically saying, for example, we need to be able to enumerate this thing. So we need to be able to get the next one. So then there would be some like function like next or something that needs to be implemented for this.
Right.
And that way you can really go much further. But at this point, we've basically covered everything that you need to be able to understand like making basic types and stuff in something like Elm. And then the main other part, which we covered on the beginning, is how you can make your own data types. Like you can do something for Monday, like day of the week.
It only took 2 hours. So if you watch 2 hours, you can learn everything you need for Elm in a video class.
Yeah.
It's not bad. Not bad.
Yeah, I'm pretty sure there are like more streamlined ways or faster ways to get through this than to listen to our rambling. But
that's I find I don't know. I personally
it's
find the way that I learn is like I need things to interrupt me. Like I don't like just straight content like consistently. Like even when I'm reading, I reread the same paragraph like multiple times. So that's why I was doing like the images, because I'm just like, what would be funny to like kind of break up this thing into the next logical thing, so we can like stamp on like this is like kind of the theme of what we're talking about. But I thought it was pretty good.
To give you some time to let sort of the ideas sink in.
Yeah.
To really think about it, because there's some like subtleties which are a bit weird, like the partial application and why we write an arrow between every argument, because like the whole idea of every function only taking one argument is really weird.
Yeah, that's not standard. Anyone who's familiar with the C family language is like, you're not going to see that.
And we haven't even touched on the fact that functional programming languages do not have variables. Like at all.
Yeah, right. They're just types.
Like you only have constants and functions.
Yeah.
That's your... We don't need these pesky variables. They introduce side effects.
What do you call XY in like Func XY? What are those? Are those parameters?
Yeah, those are parameters. Or like
I think you can I think that's pretty congruent with saying that they're variables. But it's like a constant variable.
Well, yeah.
Oh, constant. Right, yeah, it's constant, yeah.
They're constants which are different each time, so in that sense
for the scope of Func, it's like constant.
They're not really materialized. They're like, oh, it's a rewriting step.
I guess
like
that's
whenever
fair,
you
yeah.
plug into X, rewrite X with that everywhere.
Yeah.
So in that sense, it is not a it is not a variable, because a variable is a thing which contains some like, which represents some bit of memory which you can like change and update later. You cannot update X ever. Like you can set it once, and then that is what X is for this function, and it will stay that, and it will be the same.
Right. All right. Well, this is very good. I like this. This is a very good explanation. I hope your class, you did well in your class on programming languages.
Well, I did get a 10 for advanced programming, so
very good. All right, so the next chapter of this series is going to be learning Elm, now that we know the basics of type theory, and we are going to try to make
the basics of Elm.
Basics of Elm. What can
basic introduction.
What are we going to hope to be able to do after learning Elm? What is like an encouraging, what's the motivating example that we're going to strive for? Like you can use these like type safe things to do things, but
of course, you cannot mention the fact that you do not have any runtime errors.
Mm.
You will never have a undefined in your code.
Never
think
have an
personally
undefined. Wow.
For me, the biggest pull towards Elm is that Elm completely replaces HTML, CSS, JavaScript.
Mm-hmm.
So you don't have
But
to
doesn't
deal
remove them.
any
You
HTML,
still can
any
use
HTML.
them when you need to and want to, which is I find very important.
It has some like interoperability with
Yeah.
them, but it completely replaces them.
Yeah. If you
Like,
so
you will
choose
get
to
your
completely
own-
commit to
own-
Elm, like that is an avenue that you can go down.
Yeah.
Very
I
cool.
do find it works best. If you're already an HTML expert, there are some like when we're doing the introduction, we're gonna use a library that actually replaces the HTML and CSS part as well, because it's a really good library, which you technically don't have to.
Mm-hmm.
So then you would only replace the JavaScript part, which is still a big benefit. And there's still some things which are like illegal HTML to express in Elm where it would be legal otherwise, because it's just like really weird or buggy or undefined
Mm-hmm.
with always some escape hatches. But the sheer fact that you don't have to deal with like CSS 4 different ways to have the same thing.
Sweet Jesus, yeah.
Three of which are deprecated, one of it
Oh no.
which only deprecated recently, so these old browsers still need that one because they don't support the new one yet.
They're deprecated because the owner's like he died in real life, and now it's like there's no maintainer for the project.
Yeah, we don't want to deal with this. We want
Yeah.
to use our own like abstract thing where we can say, hey, all this implementation stuff, that's not our problem. Go
Yeah.
figure it out.
Right. All right.
And like there's some like general, like Elm has a very strong philosophy on certain points,
Mhm.
which I really like, which might not suit your workflow the best.
Yeah,
In
I'm
the same way
I'm
that like
curious
this
to
whole
see more.
if we think back of the graph of like effort over time,
Mm-hmm.
functional programming does take a bit more effort up front,
Yeah.
but really pays off in the late end.
Now, what
'Cause you,
I'm interested in knowing is with that graph, if like ML can change the story on that as it relates to functional programming. Like, are there tools that are just like kind of like out of reach that will like change the velocity of a developer, even if they're not as familiar with functional programming, to be able to arrive at a functional solution more easily? Because ChatGPT has been really encouraging in that regard of those types of problem solving things to help someone out. That would be something that I would be really interested in understanding more of.
Well, if I can give a small example, I had to write a compiler in Haskell
Mm-hmm.
For a C-like language, and I had some abstract syntax tree, and I needed to write a pretty printer that could show our expressions nicely.
Right.
In order to do that, I just gave the formal, like, here's the data type of Haskell, give me the pretty printer, and it wrote me 90% of a pretty printer. I just had to add in some next lines somewhere.
That's sick.
And it worked. So that was completely my machine learning, which certainly helped.
Yeah.
Although, if I were to say, like, where can we improve stuff, this type system gives you a lot of information. And the amount, like, of useful errors, and then I'm not talking about, like, oh, we're going to detect this mistake as well. More like, hey, if you detect this mistake, can we, for example, try different configurations of the functions that you have available to make the types
make it work? Wow, that's interesting.
So,
like just like shoving those things in and presenting options to someone of like, is this what you meant?
Yeah, so like, hey, your types don't work, but if you place your brackets differently, now suddenly the types work. Maybe you meant this, or like,
Mm,
hey, you're doing. If we flip these arguments, the types work. Did you mean this?
that's really
Or
interesting.
sometimes like, hey, what you're doing now makes no sense, but judging by the functions that I have available, this at least gives you the right type.
Right.
That can be hugely helpful, especially since that is a technique if you do not do that with machine learning, but you do
Yeah.
that with
Yeah.
like proper algorithms, you can start to really rely on that and basically program something and then don't complete it fully or don't bother writing any brackets. Click compile and just be like, yeah, that's the brackets I meant. Copy paste. I am done, which
Mm,
significantly lowers the barrier of entry. So, in that respect, I have much more faith for the, at least for the near future, think next 5 years, for more like stepwise approaches in like doing this. So, not machine learning, but more
yeah.
classical computing. And I think Elm is a really good example of something that does this fairly well already.
Mm,
For example, one of the things that makes Elm have one of the best image error messages, in my opinion, is that it will, depending on the mistake you make, actually link you to the documentation of, oh, if you do this wrong, you will probably get this error.
wow.
So, for example, if
And
you
that's so
use a function
simple
that does,
too. That's so simple, but it's all but absent in most like pretty much any language. I don't think I've ever seen a language link you to like the common reasons why you see this error.
for example, if you use a function that doesn't exist,
Mm-hmm.
it will link you to, hey, this is how import declarations work,
I see. I see.
which is incredibly useful because I ran into a program where I had two libraries that had an internal function that had the same name. So I needed to very explicitly import the one that I needed.
Yeah.
And in order to do that, I was like, I have no idea where to start with this. But in the error, it pointed me to the documentation that this is how import declarations work.
Mm.
And the documentation of Elm in general is, in my opinion, very well written.
Mm.
It certainly beats the hell out of a Java doc.
Yeah.
And
Are
there's a lot of like other stuff like this which isn't in itself not very meaningful or very big, but when you combine them and actually use them can give you such a nicer experience
mm.
because it really feels like he has a somewhat like he has a blog post saying compilers as assistants, and that's really how the Elm compiler feels. It feels more like an assistant than most compilers, which almost feel like an adversary, which only tell you
Yeah.
wrong,
That's
wrong.
a really good analogy. That is they are adversaries. Like I think that's why people don't write in types is cuz types are perceived as an adversary. It's something taking away from their time versus
Yeah,
something that could remotely add value to them.
they're like bad programmer. You made a mistake.
Yeah, right. Negative
Well,
reinforcement.
Elm tries to like flip this on the head and be like, hey, we've been trying really hard, but maybe you meant this, or
Yeah.
to put it in a much lighter feel and to spoil a tiny bit of what you can do in Elm. And I'm gonna make this really quick and vague, so you
Mhm.
might actually be inclined to look at that one.
That's very cool.
They have something called compiler driven development,
Mhm.
which is basically if you add something, you do not wire it up, you just click compile and you solve the errors until you're done. And this approach, because the error messages are so useful, works for like really big projects where you can do like some really big high level change and just follow the errors and so like use 20% of your brain capacity to actually solve the errors in a reasonable way. And then at some point it will compile, it will guarantee you no runtime errors, and it will just work,
Mm.
which is absolutely lovely.
That's very cool. I'm gonna take a look at the compiler more because I'm interested. It's been a while since I've looked at any type of compiler. All right, so I'm gonna stop the stream now, and then, all right, so I'll say bye. Bye to everyone who's watching. I don't know if there's anyone that's still watching, but goodbye, everyone.